Hello viewers, in today's session we are going to discuss another important and conceptual problem from three-dimensional geometry. And here we are going to solve this problem where we have to find the distance of the point whose coordinates are 2 comma minus 2 comma 3 from this plane whose equation is given by 2x minus 3y plus z minus 6 is equal to 0, and we have to find the distance of this point from this plane measured parallel to the line whose direction cosines are proportional to these numbers, that is 3 comma 4 comma minus 1, right? So here we have to find the distance of this given point from this plane, right? And the distance has to be measured parallel to the line whose direction cosines are proportional to 3 comma 4 comma minus 1. So here we are not going to find out the perpendicular distance of this point from this plane, right? So the perpendicular distance of this point from this plane is different from the distance of this point from this plane measured parallel or along to the line whose direction cosines are proportional to 3 4 minus 1, right? So let us first quickly see the definition of direction ratios, and then we'll draw a rough diagram of this problem to find out the distance of this point from this plane with this condition. So now here we are given a plane say pi, and the equation of the plane is 2x minus 3y plus z minus 6 is equal to 0, and we have to find the distance of this point, say point P, 2 minus 2 and 3, and we have to find the distance of this point P from this plane pi. Suppose this is the distance, and this point A is the point of intersection of this line PA with this plane pi, right? And later on we'll find out the coordinates of this point A, right? And this PA, that is this line PA, is given to be parallel to this line L. Say this is the line L whose direction cosines are proportional to these numbers 3 4 and minus 1. So we have to measure here this distance, that is PA, along this line L whose direction cosines are proportional to 3 4 and minus 1. So now, according to the definition of direction ratios of a line, we know that if the direction ratios of a line are A, B, C, and the direction cosines of the line are L, M, and N, then we know that A is equal to lambda L, B is equal to lambda M, and C is equal to lambda N, where lambda is not equal to 0 and lambda belongs to the set of real numbers. So now the direction cosines of this line L are proportional to these numbers 3, 4 and minus 1, right? So the direction ratios of any line which is parallel to this line L are given by A is equal to 3 lambda, B is equal to 4 lambda, and C is equal to minus lambda, right? So the direction ratios of any line which is parallel to this line L are given by the numbers 3 lambda, 4 lambda and minus lambda, right? So the direction ratios of this line L may be taken as, say, lambda. If we take lambda is equal to 1, so we have 3, 4 and minus 1. So here it is important to note that since lambda is a non-zero real number, so for any line there are infinitely many sets of direction ratios. And when we take lambda is equal to 1, then we have A is equal to L, B is equal to M, and C is equal to N. So for any line, the set of direction cosines is also a set of direction ratios, right? So here the direction ratios of any line which is parallel to this line L are given by these three numbers, and for lambda is equal to 1, we have the direction ratios of this line L as 3, 4, and minus 1. So now if we assign different values of lambda to this set of numbers, then what we will get? We'll get a set of parallel lines, right? And here the distance of this point P from this plane pi is PA, and PA is parallel to this line L, right? So the direction ratios of this line PA may also be taken as 3, 4, and minus 1, because we know that parallel lines have proportional direction ratios, right? So now we can easily write the equation of PA in symmetric form. So equation of PA is now x minus x1 over A, y minus y1 over B, and z minus z1 over c. So a, b, c may be taken as 3, 4, and minus 1. So a, b, c denotes the direction ratios of PA, and x1, y1, z1 is our point 2, minus 2, and 3. So this form of equation is known as the symmetric form of the equation of a line. So we have x minus 2 over 3, then we have y plus 2 over 4, and z uh, that is z minus 3 over minus 1. So this is the symmetric form of the equation of this line PA. So now our next aim is to get the coordinates of this point A, which is the point of intersection of this line PA with this plane pi. So let us introduce here another scalar or a real number, say R. So R is, it belongs to the set of real numbers, and the coordinates of any general point lying on this line PA may be obtained like this: x minus 2 over 3 is equal to R, then y plus 2 over 4 is equal to R, and z minus 3 over minus 1 is equal to R. So we have three equations. So let us solve them for x, y, and z. So we have x, y, and z. So x is 3r plus 2. So here we have 3r plus 2. Y is 4r minus 2. And z is minus r plus 3. Right? So for some value of r, the this coordinate is represented by this point A, right? So the coordinates of this point A may be taken as 3r plus 2, 4r minus 2, and minus r plus 3 for some particular value of r. So the next our next aim is to get the value of this r. Now at this point A, it lies on the plane pi. So this coordinate must satisfy the equation of the plane. So substituting x, y, z as 3r plus 2, 4r minus 2, and minus r plus 3 in this equation, we have now 3r plus 2, then minus 3, 4r minus 2, and then we have minus r plus 3, and minus 6 is equal to 0. So this is a linear equation in R. So we have 6R plus 4 minus 12R plus 6 and minus R plus 3 and minus 6. So 6R, 12R, minus 12R and minus R. So we have minus 6 and here we have minus 7. So minus 7R, 6 plus here 6 and 6 get cancelled, and 4 plus 3 is 7, and minus 7R is equal to minus 7. So R is minus 7 over minus 7, that is equal to 1. So for R is equal to 1, this coordinate represents this point A, which lies on the plane pi, and this point A serves as the point of intersection of this line PA with this plane pi. So now taking r is equal to 1 in this coordinate, we have x is equal to 3 times 1 plus 2, that is 5, and y is 4 times 1 plus minus 2, that is 4 minus 2 is 2, and z is minus 1 plus 3, that is 2. So we have the coordinates of A as 5, 2 and 2. So now we can easily find out the distance, that is PA, by using distance formula. So now if we take this point P as x1, y1, z1, and this point A as x2, y2, z2, then according to the distance formula, the distance PA is square root of x2 minus x1 square, and then we have here y2 minus y1 square and z2 minus z1 square. So we have now here x2 is 5, so 5 minus 2 square, then we have 2 minus minus 2 square, and then we have 2 minus 3 square. So this is 5 minus 2 is 3, so 3 square. This is 2 plus 2, 4, 4 square, and here 2 minus 3 is minus 1 square. So this is 9, this is 16, and this is 1. So this is 25 plus 1, 26. So we have under root 26 units. So the distance of this point P from this plane pi is square root of 26 units. And remember here this distance is measured along this line L, right? So the direction ratios of this line, that is PA, and this line L are equal or proportional. And remember this distance is not the perpendicular distance of this point P from this plane pi.